here's a motivating question, just to get us thinking about the topic. So suppose that there are 200 students for Calculus 1, okay? And there's 7 different sections, okay? And obviously, if you do a section of a course, okay, this is maybe not completely realistic, but certainly if I'm going to teach a course, there better be at least one student in my section, okay? Of course, probably, maybe at UVic they have more restrictions than that. Maybe there has to be, at least 20 students or something. But anyway, so the question is, how many ways can I assign the students into sections such that every section has at least one student, okay? And here we're going to have no maximum class size. So maybe I could put 194 students into the first section, and then I put one student in each of the others, or you can divide it up pretty much evenly into 7 sections or whatever. So how many ways can you do it? And believe it or not, we're going to be able to answer this question by the end, or actually before the end. So let me make this a little bit more formal by defining something called a surjection. So have you heard of these words like surjection or onto functions, like one-to-one and onto and stuff like that? Yeah, okay. So people have seen this in 122. I'll just kind of briefly review it in case people have forgotten. But we say that a function f from a set x to a set y is surjective, or f is a surjection, or it's onto, if for every y and y, so little y and big Y, there exists x and x such that f of x equals y. Okay, so if you have forgotten your stuff from 122, this is a brief reminder. So as an example, if I let x be the set a, b, c, d, y is the set 0, 1, 2, and if I define f of a as 0, f of b is 0, f of c is 2, f of d is 1, then f is a surjection. Why? Because, the way I kind of think about this in my head is kind of informally, everything in y gets hit by something, by the function. So in other words, if I take something in y, like the number 2, if I think of the function as mapping the things in x to the things in y, then the number 2 gets hit by f of c, right? F sends c to 2, okay? And the same is true for every other element of y. So 1, if I take the element 1, that gets hit by d, and 0 gets hit twice. So we don't care about things getting hit. It's okay for things to get hit multiple times, but everything has to get hit at least once. So hopefully it's clear, this is kind of similar to the problem with calculus students in sections, right? I've got 200 students. I have 7 sections. If I assign each student to a section, that's like a function from the students to the sections. And if every section has to have at least one student, then that's just a surjective function, basically, right? Or it's an onto function. So these words will be used interchangeably. Is that clear? So the thing I want to address here is counting surjections. So suppose that x and y are finite sets. The question I want to address is this one. How many surjections are there from x to y? Right. This has been the theme of this whole part of the course, right? How many ways are there to do this? How many ways are there to do that? So how many ways are there to define a surjective function from x to y? So if you don't like functions, then you can think of all of these things in terms of string, right? So here's an alternative way of thinking of this. Suppose that the size of x is n, the size of y is m. Then counting surjections from x to y is the same as counting strings of length n from or using the alphabet, which is the numbers 1 up to m, that uses every letter at least once. So do we see why this is the same thing? Because if you think of, the size of x is n, the size of y is m. Of course, it doesn't really matter what the actual elements of x and y are, because, it doesn't matter what the names of the elements are. It just really matters what the size is, right? So if I could think of x being the numbers 1 up to n, and y being the numbers 1 up to m, right? And this is something that goes back to the first class of the whole term, that a function from 1 up to n to 1 up to m is really just a word. Because, I mean, it's kind of in one-to-one correspondence with words. It's, counting these things is the same as counting words, because like if I take f of I is the ith letter of the word, right? And then if I take a function f from x to y, you can get a word by taking fi to be the ith letter of the word. And so this is just a correspondence. So really, this thing about counting surjections is the same as counting words or strings, where where every letter gets used at least once. Is that clear? So that's just just giving two different perspectives on this thing, which can be kind of useful. Okay. Does anyone have any idea how to count these things? Well, actually, let's maybe think of some specific examples first. So, right. So the question we're trying to answer is, how many surjections are there from a set of size n to a set of size m? Or equivalently, how many strings of length n are there which use every letter in the alphabet 1 up to m? So what if n is equal to m? And yeah, we've got an answer coming in the chat. Do people agree with that? Any other ideas? Like if n is equal to m? Okay. Well, I'm glad to see no alternative answers for this one, because that's the right answer. So if n is equal to m, well, I can write this as either n factorial or m factorial. They're the same, right? So the answer is n factorial, or as was given in the chat, m factorial, because n is equal to m, so they're the same. So why would this be the case? So I'm trying to make a string. I've got n letters. I'm trying to make a string of length n that uses every letter at least once. Yeah, so basically, here's the thing. If the string has length n and I have to use every letter, well, I can't actually use a letter twice, because, if I'm only allowed to use the letters 1 up to n. I have to make it have length n. If I use the letter twice, then some other letter won't be used. So this is, so it's just equal to the number of permutations of 1 up to n, because every letter is used exactly once. Because if every letter is used at least once, and there's only n, the length is only n, you have to use everything exactly once, because if you use something twice, then by pigeonhole, actually this is a pigeonhole argument basically, if I use some letter twice, then there'd be another letter that gets left out, right? Okay. So then the trickier thing comes when, this isn't tricky. What if n is less than m? So the length, for example, if I have a word of length 2 using 3 letters. Yeah, this is a little bit of a trick question, this one, because actually the answer is 0. Because if I say I have 2 spaces and I'm supposed to use, everything in like 1, 2, 3, well, that's not possible, because the length of the word is only 2, right? So this is 0. Okay, just a bit of a trick question. I mean, not really a trick question, but so this case it's 0, because there just isn't enough space to use all the letters you need to use. Okay, so the interesting case now is when n is bigger than m. So here we've got n, which is the length, right? M is the alphabet size, and n is bigger than m. If you kind of play with some examples, right? A basic kind of interesting example is just n equals 3 and m equals 2. If you play with that, you can see that the answer is 6. So I don't know. Basically, there's various ways you could do this. You could say, okay, let's look at the ones that start with a 1, right? For example. And then you know that the rest of the string can be anything except for 1, 1, right? And so you have 3 different choices. And then you could look at the things starting with 2 and whatever. Okay. I wouldn't suggest doing it this way, but this is a way you could do it in this small case. But your life gets a little bit more difficult pretty quickly. So even if I take, n equals 4, m equals 3, you can see if you start listing out the different cases that it's actually going to start getting pretty big. So this is just all of the different cases, I think, where the first digit is a 1. I guess in theory, if I've done all the ones with where the first thing is a 1, I could just multiply by 3. But anyway, basically you don't want to do these things by hand, right? So as usual, we want like a general technique for determining the answer. Okay, so here's what I want to do. So, okay, just again, what we're trying to do is count words of length n that use every letter from 1 up to m at least once. Anyone have an idea about what you would want to do? So I've got 2 words written here anyway, but this is, I don't know, for some reason this is like my permutations. Permutations, it's not really like permutations, right? If I look at the previous examples, like look at the case n equals 3, m equals 2. So n is the length, m is the, complement is good. Yeah. But so just to make it clear, n is the length of the word, n is bigger than m. M is the alphabet. So you're going to have lots of things repeating. So it's not like, there might be a way to think about this with permutations, but it's not really like permutations because permutations only use everything once, at most once. We're trying to use everything at least once. So actually this is kind of related to permutations, right? In a permutation, so just to make this clear, so to get the difference, each letter appears, so it actually is kind of a similar concept, but they appear at most once, but we want each to appear at least once. So it's a little bit different. So I like counting the complement. This is, for whatever reason, like I just seem to like this trick. Well, mostly because it seems to work a lot. So let's count the complement. What do I mean by that? Remember, counting the complement, what you do is you count a bunch of stuff, which includes everything you wanted, but some stuff that you didn't want, and then you subtract the stuff you didn't want. So to count, like the thing I'm going to count, which is extra, is I'll just first start by counting all of the strings of length n from an alphabet 1 up to m. So how many are there? So this is now like super review. We've done this a million times by now, but let's just ask it again. So how many strings of length n are there from an alphabet 1 up to m with no restriction? Anyone? No restriction. So write down any string you want, length n, alphabet of size m. It's something like what is written in the chat. Yeah, it's you got to keep these, you got to try to get these things straight, I guess. Like it's going to be either one or the other, n to the m, m to the n. I guess in theory, if you just write one of them, you'll have a 50-50 chance. But yeah, so it is m to the n. The way to think of this is, again, this rule of product. So if I've got kind of n things I'm choosing. So like there's n positions, and I have m choices for the first, m and m for the second, and m for the third, all the way up to n, like to the nth. So it's like m times m times m times m times m, blah, blah, blah. Okay. I guess you could, if you want to quickly determine which of these is correct, you could just think of the case when n is 1, right? If n is 1, a string of length 1 from alphabet 1 up to m is just going to be m choices, right? So if you wanted to quickly determine which of these is correct, just think of the case n equals 1. Okay, so now we have to throw away the words that we didn't want to count. So what are the words we didn't want to count? Well, some of the words of length n, they don't use the letter j, for example. So j is something between 1 and m. So we want to, if a word doesn't use the letter j, we want to throw it away. So how many words of length, of length n do not use j? So again, any volunteers? So yeah, so it's not much different than the last one, right? m minus 1 to the n, because basically it's just counting words with an alphabet of size m minus 1, because the only rule is that you're not allowed to use j. Okay, so then what we might think is the right thing to do, right, is just take the entire universe of words, m to the n, and then subtract the ones that don't use j, and go through all the different values of j. Sounds plausible, right? So in other words, remember, so counting the complement, we count all the words, which is m to the n, and then for each j, I want to subtract the words that don't use j, and that doesn't depend on j, right? It's just m minus 1 to the n for every value of j. So actually this just equals m to the n minus m times m minus 1 to the n, because this m comes from summing over all j. So is this correct? I suppose if it was correct, I would probably just say so, right? But does anyone see why this is wrong? It's a bit tricky, maybe. I mean, it feels right? I take the things I take too much stuff, I subtract the things I didn't want to count. Yeah, exactly. So there's a thing in the chat saying the intersection is removed too many times. Yeah, so what the thing to think about is, like, suppose I have a word that doesn't use the number 1, but it also doesn't use the number 2, the letter 1 or letter 2. Then when I was counting the things that don't use 1, I threw it away. But when I was counting the things that don't use 2, I threw it away again, right? So I've subtracted it twice. And even worse, if it didn't use 1, 2, or 3, I've subtracted it 3 times, right? So yeah, we've double thrown away some stuff. So we need to kind of add it back in. Okay, and this is exactly the same kind of logic we were doing last time. So it's really just an application of this inclusion-exclusion formula. Okay, yeah, so this was what this was meant to say. So does this sound familiar? We've thrown away things too many times. And indeed, it should sound familiar because this is what we did last time. And that's the inclusion-exclusion principle of inclusion-exclusion. By the way, if you see some stuff like in the practice problems or in notes or anything that say pi with capital letters, what this stands for is principle of inclusion-exclusion. So that's just the stuff we learned last time. So this is just like, so you don't get confused that they're talking about actual pi or something. It's just a lot faster to write pi than to write principle of inclusion. Oh, I even spelled it wrong, but anyway. Principle, anyway, of inclusion-exclusion. Okay. So now let me give you the answer to this question of how many surjections are there. So the answer is this funny looking sum. So okay, just to state this fully. So for n at least m, remember this, if n is less than m, remember the answer is just 0. So for n at least m, the number of surjections from a set of size n to a set of size m, or equivalently, the number of words of length m using every letter from a alphabet of size m is, wait a second, I think I haven't messed this up. So there's no, oh, there is an n in here. Okay, I haven't messed that up. I think this is correct, yeah. So it's the sum from k equals 0 to m of -1 to the k, m choose k, m minus k to the n. Okay, and we're going to see how we can prove this using the inclusion-exclusion, the principle of inclusion-exclusion. And if you see this notation anywhere, like in the textbook, so there's this notation S and M. So S and M is equal to this value. So the reason for S is that this is counting surjection. Or actually, there might be another reason. I think this is, some people call these like Stirling numbers or something. So maybe the S is for Stirling. But for the purposes of this course, we could like assume that the S is for surjection if we want, but it might not be. So is it clear what I'm saying here? So right now I'm just writing this formula, but we're going to justify it in a minute. Okay. Okay. So actually, yeah, this is kind of related to this comment in the chat about the intersection. So for each I between 1 and m, suppose I let xi be the set of all words of length n from the alphabet 1 up to m, which do not use the letter I. So xi is the words that do not use I. Okay, so what we want to do is count, we want to count like all the words, which is m to the n, minus the union of the xi's, right? This is going to be, our final answer is going to be equal to this because of counting the complement, right? We take all the words and then subtract the words that miss some letter. Okay, so this union can be computed using inclusion exclusion. And here's the thing. So let me pose a question for you. So I take a set S in the a subset of 1 up to m. Oh, and maybe I need to say that S is not the empty set. So if I look at the intersection of the xi where I is in S, that counts the words that don't use any letter in S. And how many words are there? So, okay, so if you don't understand the rest of this intersection stuff, it doesn't matter. I fix a set of a set S, and I want to know how many words don't use any letters from S. Is it clear what I'm saying here? So this is kind of, remember we've done this before. We've already done this where I was saying how many words don't use the letter J, right? And now we're just kind of doing this more generally for, for a set S, which might have more than one element. So how many don't use letters in S? And yeah, this is something we can figure out just based on the usual principles, right? So if I say that you have to make a word of size a length m, and you're not allowed to use anything in S, well, that's kind of just it's just a normal, a usual kind of word, right? Except that your alphabet now has size m minus the size of S. So it's just a word of length n where the alphabet m minus the size of S. And so, of course, like, it's the usual thing where you've got, m minus S to the power of n, okay? And remember, we have to remember how, to get this in the right order, right? It's the base of the exponent is the alphabet size, and the exponent is the length of the word. Okay, so I think that most people kind of got that. Okay, so what we want to do is compute the size of this union, right? And, well, we know how to do that because we know how to do inclusion exclusion. The inclusion exclusion formula, which I suggest memorizing or at least practice using it so that you know how to solve these problems. So there's lots of practice on this in the practice problems. So it's equal to the sum over all subsets of 1 up to m, which are not empty, -1 to the s plus 1, the size of the intersection over all I and s of xi. Or in other words, it's equal to, like, you add up all the x1 up to xm. So if this is an easier way to think about it, right? And then you subtract the intersections of pairs of them, right? So minus blah, 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 take every pair, then add in the three-way intersections, then subtract the four-way intersections, like keep switching between plus and minus until you get to the end. Okay. But yeah, and we've already computed this value. Remember, we just said that this is the words that don't use anything in S, and that has size m minus s to the n. And so, of course, this only depends on the size of S. So any set S of size 5 or something, like if S has size 5, right, you get an m minus 5 to the n, right, for every set of size 5. And the number of sets of size 5 contained in 1 up to m is just m choose 5, right? So we can kind of collect up these terms based on how big S is. So S will have size between 1 and m. And if we kind of collect these terms correctly, what you get is that this is equal to m choose k, which is just the number of ways to choose S of size k, right? So this goes through all the choices of S, which have size k, and then m minus k to the n. Oh, sorry, and there's this -1 thing here. So this comes from here, and then there's a -1 to the k plus 1. Is it clear where everything's coming from here? Now, something we can't forget is that this counts the stuff we're throwing away, right? This is not the answer. This counts all the words that miss a letter, at least one letter. But we're supposed to count the words that don't miss any letters. So it's just counting the complement. So the number of surjections is m to the n minus this stuff, which, like, kind of magically, this works out to a very nice answer. So if I kind of collect these things up, or not even collect them, but if you think about it, this actually does just equal -1 to the k, m choose k, m minus k to the n. Because if you think of the k equals 0 term, so when k is 0, what you get is, so -1 to the 0 is 1. M choose 0 is 1. So it's like 1 times 1, or maybe I'll write it. So -1 to the 0, m choose 0, m minus 0 to the n gives you just m to the n. So that's like the same as what I've got here. And for all the other values of k, I get the correct thing here. It looks wrong because there's a k here and a k plus 1 there, but then you have to remember there's a negative here. So so it actually is the right answer, because -1 to the k plus 2 is the same as -1 to the k, because multiplying by -1 twice is just multiplying by 1. So I can understand maybe this was fast, I'm not sure. But are there any questions about this? So just like everything else, one way to answer questions about counting surjections is to remember the formula, right? So if you memorize this formula, that is going to help you to solve the problems. If you're bad at memorizing stuff, like I am, then trying to remember how to work it out is also useful. So I got a question about where this I assume it's this k plus 1. This comes from the inclusion exclusion, because it basically comes from here where there's a size of s plus 1. So that the size of s becomes k when you collect up all the sets of the same size. Yeah, and it's kind of annoying that this does have a plus 1 in it, but if you think about it, like, yeah, remember how inclusion exclusion works? You add up like the things where you take one thing, like x1 up to xm, those get added, and then you subtract pairs of things. Yeah, the reason there's a plus 1 is because so when you do inclusion exclusion, you want to take, like, so if I have A union B union C, I want to take the size of A plus the size of B plus the size of C, right? So meaning when I'm taking one set at a time, I want it to be positive. When I take two sets, like A intersect B, A intersect C, whatever, I want it to be negative. If I put a 2 in here, if I put a 1 in here, like -1 squared is positive. When I plug in a 2 here, it's -1 cubed, which is negative. So it's just like, yeah, it makes the formula work. And then, yeah, so then this plus 1 kind of gets carried through to there, and it gets carried through to here, and then it gets multiplied by another negative, so it can become, I mean, I could have wrote it as k plus 2, but might as well write it as k because it's simpler, because of this. It's a little bit of algebra and a little bit of, thinking about how inclusion exclusion works. Any other questions? Yeah, so the notation in like the textbook and stuff is S and M, right? You can think of that as surjections from a set of size n to a set of size m. Okay? Okay. Yeah, so like I said, like, actually, yeah, maybe in this case, like, I think for most problems you can just remember the formula, but I think there will be some problems, I think maybe there's even one on the assignment, where you're sort of asked to kind of go through this argument, this inclusion exclusion argument, to count something which is similar, maybe not the same, but a little bit similar. So not only do you have to kind of understand the formula, but it is valuable for you to understand how this proof worked. So I suggest kind of looking over it and thinking about it. Okay, and just to get a bit more practice, let's now do something which is actually pretty similar. So it's something called derangements. So here's a kind of motivating question, which is completely not realistic because I don't know anyone who'd have this kind of party. But imagine you go to a party where, as a fun activity for some reason, everybody brings a hat to the party, and the rule is at the end of the party, when you leave, you have to take somebody else's hat. Okay, so you're not allowed to take your own hat back. Don't ask me why anyone would want to do this. Personally, I don't even really like wearing hats. But yeah, for whatever reason, this is the party. I hope I'm not offending anyone who actually has hat swap parties. But yeah. So how many ways are there to do this in terms of, like, how many different outcomes are there in terms of different people having different hats? Okay, is it clear? So everyone brings a hat. all the hats are different. Like they're distinguishable hats. So somebody has a cowboy hat, somebody has a baseball hat, whatever. And you have to leave with a different hat than what you came with. How many ways can I do this? And that's something called, well, that's related to the concept of a derangement. So a permutation of 1 up to n is called a derangement if for every I from 1 to n, the ith element is not equal to. So for example, if n equals 2, there's only one derangement, right? Well, so if n equals 2, the permutations I have are 1, 2 or 2, 1, right? The first one is not a derangement because the ith position is I for all I, actually, whereas the second one is a derangement, right? For, let's say n equals 3, you've got like 1, 2, 3, not a derangement, 1, 3, 2, not a derangement, because the 1 is in the first position. But for example, if I take 2, 3, 1, that is a derangement because the first position is not a 1, the second is not a 2, the third is not a 3. So you can think of the hat swap problem as asking to count derangements because it's like saying, basically if I'm the ith person and I take the jth hat, that's like a permutation where the ith position is j, if that makes sense. Okay, is that clear, or is it clear what a derangement is? So it's a permutation where the ith element is not I. Okay, so this is now, you get a sort of similar formula for the number of derangements, similar to the thing about surjections. So this is a formula which now I'll just state, but then I'll give you a proof. So the number of derangements of length n, is equal to this formula, which is n choose k, negative 1 to the k, times n minus k factorial. And remember, we gave some notation for the surjections, which was SNM. The notation we'll use here is dn. So dn equals the number of derangements of length n. Is this clear? So this right now is just a statement. I haven't proven it, but we will prove it. And unsurprisingly, the way I want to prove this is using inclusion-exclusion, right? Same as usual. Same as for the surjections. Okay, where should I start? Does anyone have a suggestion? So, well, maybe that's not a very clear question, but yeah. So, okay, there's a suggestion in the chat, number of strings where the ith letter is I. Even before that, but yeah, it depends whether you count this as the first step or the second step. But, I also could just say, like, I want to count the complement. So I take all the permutations and I subtract these things. But yeah, the things I'm going to subtract, the first step is going to be the permutations where the ith letter is I, right? That's totally the right kind of thing to be doing. So very similar to counting the surjections, I'm going to define a set xi to be the set of all permutations whose ith element or ith letter or whatever is I, right? So these are the things we don't want to count, okay? So here's a question. Well, first of all, let's just say, just as a sub-question, how big is xi just by itself? How big is xi? So how many permutations are there of 1 up to n, let's say where the first element is 1, let's say. So maybe scratch that. Just say, how big is x1? So the permutations where the first element is 1. Yep. So maybe I should make more of these things into polls to give more kind of interaction. But yeah, so I appreciate the participation here. So it's n minus 1 factorial, right? Because if I've chosen the first element to be 1, then I've got n minus 1 more elements to choose or to permute, and I know that these entries are going to be the numbers 2 up to n, right? So I've got like n minus 1 symbols that I'm writing each of them exactly once, so there's n minus 1 factorial ways to do it. And so similarly, if I ask how large is this intersection, it has size n minus the size of s factorial, right? Because so everything in s gets fixed. Like if 1 is in s, then 1 goes to 1. Like if 3 is in s, then 3 goes to 3 and whatever. And then I've got n minus s positions, which I'm going to put all the other letters into exactly once. Okay. And maybe it takes a bit of thinking, but or maybe not. But even in the case where, it's always good to check the kind of boundary cases, but even in the case where, what if s is all of 1 up to n, right? So what I get here is 0 factorial, which is 1, right? And that's actually correct because, so what is a permutation in all of the xi's, right? It's just the permutation where every element goes, the ith element is I for all I. So it's just the permutation, 1, 2, 3, ... up to n. So there's just one permutation. Okay, this is just a sanity check. But yeah, this is the answer to this. Is it clear? So these are things, by the way, if you practice more, you really, it'll benefit you a lot to be able to come up with these things really, quick, because, and that just really comes with practice and experience. Okay. So now by inclusion exclusion, our favorite trick, what we can do is we can write this as the sum overall non-empty subsets of 1 up to n of -1 to the s plus 1. Remember, there's this weird plus 1 here because, we want to start off with positive and then negative rather than negative and then positive. Intersection I in s xi. And we know what this is. We've already computed it. This is just n minus the size of s factorial. And now exactly the same way as we dealt with the surjections and stuff, we can collect this, the key thing here is that this expression here doesn't depend on really the specific set s, but it only depends on it depends on the size of s, right? It only depends on how big s is. So basically we can group these things based on how big s is. So if s has size k, you get n minus k factorial. Here you get a -1 to the k plus 1, right? This is the case, the size of s is k. And how many sets of size k are there? Well, there's n choose k. So we can break this up as the sum of k equals 1 up to n. It doesn't matter what order I write these things in. I'll write n choose k because that counts how many sets there are. -1 to the k plus 1, because that's, when the size of s is k, that's what you get here. N minus k factorial, which is what you get here. And you have to not forget with these things that this isn't the answer, right? This is the answer for what we want to throw away, right? So the final answer is you take all of the permutations, which is n factorial, and you subtract the ones you didn't want, which is the thing we wrote on the previous slide. And now if you check that, again, magically, this turns out to have a nice formula. So I can now write this as the sum of k equals 0 up to n, n choose k, -1 to the k, n minus k factorial. Because if you check, if I look at the case k equals 0, what do I get? I get n choose 0, -1 to the 0, n minus 0 factorial, which is just n factorial. So that gives me, the k equals 0 term gives me the n factorial. And then all the other terms just come from this sum. But you have to remember there's a k plus 1 here. There's a negative sign, and -1 to the k plus 2 is the same as -1 to the k. So that, just a little bit of kind of algebra to make the sum look nicer. Are there any questions about this? So hopefully you can see that these things are pretty similar. If that, didn't make any sense to you, I really suggest looking over the inclusion exclusion, because you're going to see problems involving inclusion exclusion, but you might see problems involving this stuff like derangements and surjections, and basically the basis of that is all inclusion exclusion, right? So if you have a shaky understanding of that, then it's going to make this stuff harder too, basically. And also the basis of everything is these rules of product and counting the complement. So that's a difficult part of this course, is that a lot of things build on top of each other. So it's important to get the foundations. But are there any questions about anything? So again, you can just remember the formula, or you can learn how to derive it Okay. So let me now tell you something cool about derangements. Okay, and coolness is obviously in the eyes of the beholder, but to me it's cool. Okay, it doesn't have to be cool to you, but let me tell you something cool. So we've got this formula, right? dn is whatever this is. If you put in the formula for n choose k, you can see that there's some cancellation, right? Like if I write n choose k as n factorial over k factorial n minus k factorial, right? That's the same as this. You can see that this thing here, right, is the same as this, so they're going to cancel. So that gives you another way of writing the number of derangements, but why do we care? Why is that cool? Let me kind of rewrite this. So it's the sum from k equals 0 up to n of n factorial over k factorial times -1 to the k, right? This is just canceling these things. Okay, something to notice is that the n factorial can be factored out, right? So this is the same as n factorial, all times the sum k equals 0 up to n, -1 to the k over k factorial. Does this kind of sum look familiar to anybody? Like what if I take the sum k equals 0 to infinity of 1 over k factorial? Does anyone know what that is? I don't know whether you've seen this in calculus or anything else, maybe not. Like Taylor series and stuff like that. Have you seen that? Like, has anyone seen that e to the x is like this? You seen this stuff before, Taylor series? Maybe not. Maybe not. It's been a while. Yeah. Yeah, okay. I learned this stuff, I think, in first year or something at some point. So maybe you've seen this, maybe not. Yeah, so you've probably seen it, but probably don't remember it. But anyway, so if I'll tell you, like, e to the x is equal to that. Like x, yeah, so it comes from, Taylor series and stuff like that. But so if I put x equals -1, right, what you get is pretty much what I've written in this corner down here, this sum, the thing inside the sum, except that the thing inside the sum stops at n, whereas this one over here goes to infinity. But it's approximately the same thing, right, if n is very large. So what I'm saying here is, so this is just rewriting this. E to the -1 is 1 over 0 factorial minus 1 over 1 factorial, it's, in other words, e to the -1 is the sum k equals 0 to infinity of -1 to the k over k factorial. Okay, so dn is, what we've proven already is that dn is this thing, which is not an infinite sum because it stops at n. But as you can imagine, like as n gets larger and larger, the sum becomes a better and better approximation of e to the -1, right? So roughly, weirdly enough, if n is very large, or I don't even think it has to be that large, but dn is roughly n factorial over e. So if you ask, like, if I say I'm going to pick a permutation of length n, where n is large, like n is say 100 or 1,000 or whatever, I don't know what's a large number, 1,000,000, I don't know, at random, suppose I just put all the permutations in a hat and I pick one out. Well, what's the probability that it is a derangement, right? Well, there's n factorial permutations, roughly this many are derangements. So basically, if I pick a random permutation, the probability of being a derangement is roughly 1 over e, which is, I don't know. I don't have a good reason for that, apart from the formula gives it to you, right? Why on earth would it be 1 over e? But it is. It's 1 over e. Are there any questions about that? Does anyone else find that cool? Maybe not. But yeah. Okay, let's, I think this is the, don't want to give it away. Yeah, it's cool. Okay. 1 vote for it being cool. 2 if you count me. Okay, let's do an application of this. So just an example. I think probably will be done early. So let's say Math 122, which we talked about earlier in terms of learning about surjections. So it has 4 sections and 4 different TAs. Now here's the potentially scandalous thing, is that each TA is dating one student in the course. Maybe there's a bit of an age gap. Maybe I should have picked a higher level course because first years and a graduate student. Anyway, nothing wrong with that. Yeah, so each TA is dating one student in the course, and those 4 students are in 4 different sections, okay? And the idea is it wouldn't be appropriate for the TA to mark the work of their significant other, right? Because it would seem, they would be tempted to cheat to give them a higher grade, right? So how many ways can I assign the TAs to the sections so that no TA marks the work of the person that they're dating? And yeah, this is not the current situation in Math 122. This is a fictional situation. So how would I do it? So I don't know why I've got a box for the answer here. But does anyone have an idea? So even if you write it in, without writing a number, but do any of the things we've learned today have any relevance here? 4 sections, 4 TAs. We don't want the TA to mark the work of their significant other. Those people are in 4 different sections. Any thoughts? Does it have anything to do with surjections or derangements? Well, okay. I claim it has something to do with derangements. Okay. Here's how to think about it. If we have TAs and we have sections, and let's say I've got TAs 1, 2, 3, and 4, and sections 1, 2, 3, and 4. And let's say that like the significant other of TA1 is in section 1, TA2 is in section 2, TA3 person they're dating is in section 3, and TA4 is in section 4, right? What we want to do is like rearrange the TAs so if I take this, like I take the permutation 1, 2, 3, 4 of the TAs, I want to rearrange them so that no TA ends up where it started, right? If I initially I line up the TAs to mark their significant other, I want to rearrange so that none of the TAs are in the same place where they started, right? So the answer is going to be D4. Is it clear how I got that? So every TA needs to mark one section and so on. Okay, so if I wanted to actually compute it, I use the formula. Right, so remember the formula was that dn is the sum k equals 0 up to n choose k, negative 1 to the k, n minus k factorial, which also you could write as, so we kind of came up with 2 different ways of writing this by canceling, you can do it either way, it doesn't matter, it's the same, but you can also cancel the n minus k factorials, and you get n factorial over k factorial times negative 1 to the k. And that's what I'm computing here. So I'm just taking, 4 factorial over 0 factorial, 4 factorial over 1 factorial, 4 factorial over 2 factorial. And notice I've got these alternating pluses and minuses, right? And turns out the answer is 9. So the number of ways to associate TAs to sections in this case is 9.